Surface grinding process evaluation and cost analysis is a spreadsheet consisting of 5 individual sheets and an instruction sheet. We will start with the conventional sheet. Anything you see in blue font to the left of these top 3 columns and anything in a charcoal colored drop down box are critical or potentially critical data for input. So let's go through that. Our first choice is either millimeter or inch. We've chosen inch, and you'll see all input inch only. Had we chosen millimeter, all the calculations would have changed input millimeter only. If we say 0, then a lot of your data goes away from what we had. And one of the critical inputs is down here. So we'll go back to inch. The next process is, are we speaking pendulum, which would be a standard traverse rate of low depth stock removal and pretty high traverse rate, and creep feed, where you're typically taking all the material off on one pass with a very low traverse rate. We're going to pick pendulum. The next critical is spindle power, and you need to be sure to hit either horsepower or kilowatt that you're measuring. Down here, there's a very critical recommended spindle power, which comes into play when we do the calculations further down the line as to what would be the optimal feed rates based on the horsepower recommended versus the spindle power that you have. For example, if we had none, even though we input 10, there would be nothing. And this could be critical because nobody entered whether it be horsepower, which in this case is 10, or kilowatt, which would calculate the 7.5 kilowatts recommended. The next important is the contact area between the wheel and the part. In this case, it's a straight 2-inch wheel. But if we were doing, say, an index part with a form, and we were indexing around and we had a 2-inch wide wheel, but if you stretched out the contact, it might be 2.5 inches. It's critical to have that linear contact input for all kinds of calculations as we proceed. The usable depth, the radial depth of use on this particular wheel is 4 inches. We have a 16-inch diameter with 8 inches diameter, or 4-inch radial of wheel to use. You have 2 choices, either a reciprocating, and that's a standard where the part is on a table. The table is moving back and forth and also across. And you have index, which we just discussed. You would not be moving across the part, but rather the part would index around a circular process, giving you a new set of grind each time where there's really no cross feed at all. In this case, we've chosen the reciprocating, and the total pallet width, because could be multiple parts on this, is 23 inches wide across the table, and the total pallet length, no matter how many parts, which the travel of the wheel is going across the parts, is 90 inches. The CBN wheel cost for this particular test, and this is a real test that's been done out in the field, is $3,885 net to the user. It's critical, whether we're up here with the wheel cost, the conventional, or with the CBN. Now, critical here is CBN wheel specification. We have a choice of Maximizer, Maximizer ST, which are low concentration wheels. We've chosen the ST. Or we could go high concentration, which is more of a normal CBN process for high volume, or other. It could be metal, resin, whatever. We've chosen the ST in this case. If it were other, you would enter that specification. The choices for dressing are single point, rotary straight dress, and rotary form dress. The single point and rotary straight dress have most of the questions the same, except if we had chosen rotary straight dress, we would now see we need the RPM of that dressing roll and the rotary diameter. If we had chosen form dresser, then we have a lot of changes, because now we're talking the number of plunges per dress on the form plunge, the number of parts per load, but then the infeed per rotation of the wheel if form dressing. Now, had we chosen rotary form or rotary straight, then we would have entered the RPM and the roll diameter, and right next to this RPM would have been the surface foot, as you see here. And then we would have known it would have shown up the roll to wheel ratio, dividing this number by this number, and we would have a choice of picking whether it be a plus or a minus for that process. The next input, after we've now gone back to straight, is what is the infeed per pass. In this case, we're going 2/1000. Number of passes per dress are 4. The dress traverse rate is 10 inches per minute. It could be millimeters per minute had we chosen millimeter over inch. Number of parts per load or per dress is 1. Again, we've done the RPM at 1551, which is 6497 surface feet. The coolant type, also critical, is oil, water soluble, or synthetic. In this case, we've chosen water soluble oil. The next important is the nozzle or nozzles, plural, information. This will come up in a few minutes. If you look down below here, you'll see the optimal coolant flow and pressure based on input. And we've calculated based on the number of nozzles. In this case, there's only one rectangular nozzle, no round nozzles, no average diameter. The average length, in this case there's only one, was 2 inches. The average opening of the height, if there are more, you have to put the average, would be, in this case, 100 thousandths. That calculates that we need 71 GPM at 79 PSI in order to achieve a percent of 100% plus of the actual velocity and volume needed to get the coolant into the interface, which is critical in order for you to optimize your grinding process. If you go and actually at the manifold, either with a bucket test if it's applicable, or with a flow meter, measure the coolant flow, which we did here, where we have 30 gallons per minute, and measure the coolant pressure with a pressure gauge at the manifold, which we did, which is 70 psi. You have a choice here of liters per minute or GPM, psi, or bar. Now the calculations you're going to be seeing on the coolant flow calculating sheet at the end, everything is always going to be converted to gallons per minute or psi. This is not critical, but as information is important, or whether we're using Celsius or Fahrenheit, and what the degree of temperature, if you can find that out. Our next choice is time period. We have a choice of day, 1 week, 1 month, or a year. In this case, we picked a month. And the machine time, the load, everything related to not grinding. What is that? And in here is 7,200 seconds or 120 minutes just to set this up. Wheel change time in hours is 0.5 or 30 minutes. The number of wheels per process, and we could have multiple wheels. We could have a multiple head with one for finishing, one for roughing. In this case, we're doing 1 wheel. Number of parts or loads per time period. We entered 102 for this process. Present wheel cost each, meaning the present conventional wheel, was $800 net user. Labor and burden rate, very critical, is showing up at $35 an hour. Now this can range from, I've seen it as low as $25 an hour to over $125 an hour. And that's important for us to understand the true cost of this process. We have a choice now of the number of shifts, and that could be a half a day, 1 shift, 2 shifts, or 3 shifts. 1/2 shift or whatever. We're using 2 shifts. We have 2 choices of a 5-day work week or a 7-day work week. We're picking 5. Again, very critical for our calculations. Now we have to enter all the pertinent data. Stock removal total, in this case it's 15 thousandths of an inch. Total stock finish is 1 thousandths. Now we need to know what is the infeed per pass on the rough, and that's 2/10, and on the pass on the finish is 2/10. So it's very, very small stock removal that they're running. Infeed rate part length rough is 1,080. Feed rate finish per minute is 1,080. Feed rate, part length, spark out 1080. Number of spark out passes 10. Cross feed rough, percent of wheel width. So we could be going 100% of the wheel width, 25% of the wheel width, 50. In this case, all three, this is what the customer has been doing, is set up at 50. So below will be all the calculations. On your rough grind, you actually show 0.22 Q prime. And Q prime is simply, in surface grinding, the depth of that cut times the traverse rate equals the Q prime. So that shows up on both sides. Again, what we need for GPM and PSI for optimal. And this is actually the volume of work versus the volume of a wheel, which is 51.48 cubic inches or G ratio. The total grinding cycle in this process is 163.7 minutes. The total grinding cycle floor to floor is 28.37. I'm going to go through this quick because we're going to see the comparison as we go down. The next one is input sheet for CVN. In other words, we can change a variety of data that would be normally defaulted. In this case, we changed from 7 pieces per dress, which is normal. In the test, we had to run 1. So we changed that from if we had taken this 1 out, it would automatically default to a number. We have a choice of no finished stock or finished stock. In this case, we are, and we're taking off the total of 1/1000 for the total finished stock. In feed per pass, we're going to be going 5/10. In feed for finish, 2/10. Feed rate 1080, 1001, 1080. Now, see, this would have changed had we not done that. If I take this out, this number, it will default. I guess it's not to 1000, even though we were running 1080. So I input that so we actually duplicate what we were running in the test. You would see if we took the 10 out for the number of spark outs, we'd be 1. But in this case, we did 10. And then we go to super abrasives. Now, the super abrasives is actually taking all the data that we've entered in the conventional and the changes in the input data, and now calculating all the numbers. So, of course, the GPM will stay the same, the PSI stay the same because we didn't change anything there, but we could have. And we show here that we have $5,992.56 in savings. Had we been in red and a loss, it would have shown up as a red number. One of the things to look at is the additional savings or loss based on the labor and burden cost. We compare this number to this number compared to the conventional number and that number. That becomes an additional number of 1,328.81, which is added to the straight out cycle time differences. But to let you see how easy it is, if we go to synopsis, we actually show everything related to each process right next to each other. So if everything comes out good for the super abrasives, then there will be a green arrow show up on all the plus areas. So you can see, for example, the Q prime, you want to be higher if you're better, and in this case we are. If your total grinding cycle time, you want this to be less than this, which we are, and so forth, and then you see the total savings. And you can see that the percent actual compared to needed is 44%, and the present pressure is compared to PSI is 89%. And here's how we came up with that. If you go to the coolant flow, this section here is log, showing you everything that you actually entered in this process. So you'll see that it was calculated we need 71 GPM and 79 PSI. When we measured it and entered those real numbers, it shows that we're only running 44% of the needed amount for the GPM. That would be flow rate of 30 versus 71, and 89%, which would be 70 versus 79 for the PSI. So that lets you understand what you would need to do, which in this case would be probably to make a smaller opening or orifice to allow a bit more pressure and flow out of it. So this side is a coolant flow calculation that is interactive. And you can change, for example, whether you're using oil, water soluble, or synthetic. We're going back with water soluble. And we can decide if we're going to be using inch or millimeter in our input. And here, where we had 100 thousandths, just to show you how this works, if we took the average nozzle, that before was just one nozzle, had 100 thousandths opening. We changed that to 40 thousandths opening with the same width or length, 2 inches. Still one nozzle, everything the same. Now you look at if we enter what the actual flow was. Instead of GPM being 44%, we're at 111%. We still stayed at 89% because nothing changed there. So by squeezing that down from 100,000 to 40, it gives you an idea. This is actually for you to do something like that, or if you just want to play around and use this process for other applications. At the bottom, I gave you a conversion table, which takes a lot of standard product and standard calculations and converts them from metric to inch or in other areas. We also show the gallons per minute. What is the formulation that we use to actually calculate this? And we do the same thing with PSI. And there's a little explanation that we show 231 divided by wheel P line. What does that mean? Well, 231 is the cubic inches per gallon of water at sea level. That's a standard factor that's used. For P line, that is equals a linear width, or the contact of the wheel of work that the nozzle should be reflecting. What is that length? And then for PSI, that we use a factor of 0.87 as a multiplier when we're calculating a number for oil over water soluble. So I want to thank you for your time, and if you have any questions at all, please do not hesitate to write me, Dale Savington, by going to the website www.abmart, that's abmart.com, and on the Contact Us section found on the home page, bottom right, input your questions or your need to talk to me. Thank you.